Hello and welcome to Learning with Nikhil. Today we'll learn about frequency domain representation of sampling. Or else we'll do a recap of what we have done in the previous video. This is a recap. So what we basically have done in the last video was we basically this is xc of t. C stands for continuous time signal, and this is S of t. This is basically impulses, and we get xs of t. Remember that S stands for sampling or sampled, and xs of t in itself is a continuous time signal which we pass through a conversion circuit, which basically gives us x of n. And if you remember, xs of t was summation n from minus infinity to infinity xc of nt into delta t minus nts ts. So to derive frequency domain relation between the input and output, we need to consider Fourier transform of xs of t. We can write xs of t as xc of t into s of t. Yeah. So xs of j omega, see it's j omega because it's continuous time, is equal to xc of j omega convolved with s of j omega to pi. Yeah. Now we'll consider these terms individually. Xs of j omega is s of t is a periodic impulse train. So xs of j omega will be a periodic impulse train with the equation. This is in frequency domain, so it will be minus n omega s. Yeah, this will be s of j omega. So s of j omega is also an impulse train with with every impulse after omega s frequency. So substituting this in this equation, we get let me check if it's in the frame. So we get xs of j omega as 1 by 2 pi xc of j omega convolved with there is a constant term which I am writing here, 2 pi by t. N is equal to minus infinity to infinity delta of omega minus n omega s. So this will be 1 by t if you look at this is a convolution with delta. So what we will basically have in the end is minus infinity to infinity xc of j omega minus n omega s, right? Because f of t convolved with delta of t minus t naught will be f of t naught, right? So it's the same thing here. So by looking into this, what we can say is the Fourier transform of xs of t, that's basically xs of j omega, consists of periodically repeated copies of xc of j omega, right? Let's do this graphically. It would be much more intuitive. let's say this is our x c of j omega, and this is our omega, right? Now if we want to draw x s of j omega, what will it look like? So at 0 we suppose put n equals to 0, we have xc of j omega, correct, at n equals to 0. So that's basically this. Let's keep it omega n. So this is basically omega n. Now if n is equal to 1, this, I mean, the term is xc of j omega minus omega s. True? So after omega s, this just shifted. You get the same thing. Yeah. So this is omega n. So this will be omega s plus omega n, and this minus. So this will be minus omega n plus omega s. True? Similarly on the other side, and so on. This is xs of j omega. One important thing to note here is, if these two shifted I'm sorry. If these two shifted parts of xc of j omega, if they are not overlapping, that means basically this is more than this, correct? So omega s minus omega n, this is basically this, is greater than omega n, or we can say equal to also, because it can be like that. So this will give us omega s greater than or equals to 2 omega n, and this is Nyquist-Shannon theorem. NYQ, yeah, Nyquist-Shannon sampling theorem. Now the question immediately arises is, what happens if omega s is less than 2 omega n? Let's see what happens. So we have x, is it in the frame? Yeah. Now we have excess of j omega as 1 by t times, okay, I'll write it here, 1 by t times summation n from minus infinity to infinity xc of j omega minus n omega s. So for n equals to 0, it's here, this omega n minus omega n. For next, for n is equal to 1, it is at omega s. And note that omega s is less than 2 omega n, or in other words, omega s minus omega n is less than omega n, correct? So now the left part here is ends at omega s minus omega n. So, and that will, okay, let me do some correction here, let this be omega n. Now this comes like this, and the next one comes like this. Correct. So what's happening here is the repeated copies are getting superimposed or overlapped on each other. So which is a problem, because I'll tell you why it is a problem. This is a computer, okay, and from the this is the real world. Okay, say you're speaking to the computer. So basically, computer takes this analog signal, converts it into discrete, processes it here, and then it has to give back the signal, correct? it say this does nothing. It just takes it and just sends it out. Now, if this computer is not able to generate the same signal, then there's no point of using the computer. I mean, it's just waste of time. I mean, waste of time and resources. So that's why we need to have omega s greater than or equal to 2 omega n, so that these things are not overlapped and we have the original signal intact, or we have we can regenerate the original signal. And let me check if I've missed something here. Oh yeah, we were talking about regenerating the original signal. Let's see how we can regenerate the original signal. Okay, I'll redraw this again. Important condition here is, to regenerate the signal we need to have this condition satisfied. So what is this? X s of j omega, and this is omega. This is omega s 0. This is minus omega s. This is omega n. So if you want to regenerate the signal, if you remember, the original signal was just this in the frequency domain, correct? So if you want to get this signal back, you need to use a low pass filter doing that. Okay, you need to pass it through a low through a low pass filter, so that we eliminate everything else and pass only this. So we'll get back this. Correct. So I'll redraw this again here. Xc of t, you're passing it to x of t, you get xs of t, which you are passing through a filter, a low pass filter, so that you reconstruct the signal. Okay, in ideal case, xr of t should be equal to xc of t, correct? Only then the signal is regenerated back. Now for that to happen, this say this is omega L low pass. Okay, so omega L should lie between, this is what, omega s minus omega n, and this is omega n, correct? And this is very important condition. I guess that's all for this video. Remember, you are phenomenal. Bye.